We're very lucky to have Sanjoy Dasgupta from UC San Diego, and he'll talk about labeling a data set using Sublinearly.
Okay, thank you. So I'm going to be talking about some variants of the active learning problem. And just to introduce this, so one thing that's worth pointing out is, the field of machine learning, there's a whole lot of different things. Clustering, embedding, density estimation, the list goes on. But it really seems that, at least at this point in time, the one thing that it does really, really well is learning accurate classifiers from very large data sets. Okay, that is the sort of the strongest thing it does. And unfortunately, getting very large label data sets is often not easy. Okay? So this has motivated the field of active learning. It's this realization that in many problems, the common situation is that you have a lot of unlabeled data, but the labels are hard to come by. Okay, so if you're a marine biologist trying to classify dolphin clicks, you have some underwater microphone that can record hours and hours. Okay, but then some expert has to listen to these recordings and classify clicks according to the species of dolphin they're from. Okay, if you are doing computational drug design, you can come up with vast amounts of unlabeled data. Okay, libraries of virtual chemical compounds. But if you want to label one of these points, if you want to figure out whether it binds to a target of interest, a wet lab experiment has to be done. Okay, so there are all these situations where you can get all the unlabeled data you want, but labeling it is very expensive. Okay, and so the model over here is that you have a lot of unlabeled data, you don't know anything's labeled, you want to nonetheless learn a classifier from some pre-specified class H. Okay? And you only really have enough resources to get a few labels. And so the way to do this is adaptively. You ask for one of the labels, you wait to find out what it is, then you ask for another one, you wait to find out what it is, and in this way, you try and always pick the thing that you feel is going to be maximally informative. Okay? And so the question is, what are good querying schemes, and what is the trade-off between the accuracy of the classifier you get and the number of labels you ask for? Okay, so this is the setup in active learning. And what I'm going to do is to just talk about some of the work that's been done in this area. There's a huge amount of work that's been done, both on the practice and on the theory side. And I'll talk about it for about 5 minutes or 10 minutes, and then, and I think it'll then turn out that there's actually a fundamental flaw in this problem formulation, and so I'll move to sort of an alternative formulation that's sort of much better suited to sort of the way machine learning is actually done, and then that'll be the focus of the talk. Okay, so. Active learning. So what are the schemes out there? It's been studied very thoroughly in both theory and practice, and unfortunately there's a gap between the two. Okay. The sort of schemes that are used in practice are somewhat different in flavor, even at a very high level, from the ones that the theoreticians have come up with. Okay, so what are the practical schemes? Okay, so this is the way they look. Let's say you're learning linear classifiers, say. Okay, they're active learning schemes for just about any class of interest. Okay, let's say you're doing linear classifiers. You have a whole bunch of unlabeled points. You've seen a few labels so far. You fit a linear classifier to the points you've seen, and then you say, oh, you know what? The points near the boundary, those are the ones I'm uncertain about. Let me ask for one of those labels. Let me ask for the label of the point near the boundary. Or sometimes it's more sophisticated, and you say, well, these are the points I'm uncertain about, the points near the boundary. Let me ask for a label that is likely to reduce the uncertainty on these points. Okay? But the high-level idea is that you're committing to a particular classifier, and you're using it to assess what the uncertain points are and what the certain points are. Okay? So these are the practical schemes. There are a whole bunch of methods that are rather different in flavor that theoreticians have come up with. And what happens over here is that instead of committing to a specific classifier, you just say that based on the labels I've seen so far, this is the set of candidate classifiers. Based on the labels I've seen so far, these are the plausible linear separators. And I will think of an uncertain point as being a point on which this set of linear separators has some disagreement, has a significant amount of disagreement. Okay. So does that make sense? And so feel free to stop me anytime. Okay, so they're very different sorts of schemes. And you know, unfortunately, it's a pretty big gap, yeah.
Isn't the version space pretty large?
Right, the version space is very large, so it seems like doing this explicitly would be completely intractable. In the case of linear separators, you know, it's an infinite space. But people have cooked up very clever ways of doing this implicitly. By just storing the list of label points seen so far, you can then ask questions about the version space. How much uncertainty is there on this particular point? You don't actually have to explicitly. Okay. So, so how bad are these practical schemes? You know, what is the problem? Is it that they don't give you optimal rates of convergence? They aren't really choosing the maximally informative points. So it turns out that in general, they're actually much, much worse than that. I mean, forget about getting the right answer with just a few labels. They do not necessarily get the right answer even with infinitely many labels. So they're not statistically consistent. And I'll show you why that is. Okay. So so this is a standard active learning heuristic where you choose a few points at random, you get the lay of the land, you choose your current boundary, and then you query points near the boundary. Okay, so let's say the data lies in one dimension. So we choose a few points at random. Maybe we get some points from this cluster that contains 45% of the data, some points from this cluster that contains 45% of the data. So our initial boundary will be somewhere in the middle. Okay, and so the points we consider uncertain will be points somewhere in the middle. And so we'll end up asking a lot of queries over here. Okay? And as we ask more and more queries, we will converge to this boundary. Okay. Is this the optimal boundary? Well, let's see. This boundary has got a 5% error rate. Okay. Whereas this other boundary over here has only a 2.5% error rate. Okay, so this is a situation where it's not even statistically consistent. Even in the limit of having infinitely many labels, it converges to a bad solution. And so this is sort of, this lack of consistency is the problem that has dogged active learning methods.
And isn't this because you're choosing your optimum you're not using the fact that you have a lot of other samples, just unlabeled. Shouldn't be using those to find the right next classifier?
Right, so it's not making proper use of the data distribution, right, of the unlabeled data distribution. And so I'm going to be mentioning a lot of open problems because, you know, although there's some work been done in this area, I would say that it's largely open. And one of them is really to find a generic fix to these kinds of heuristics. So we have these uncertainty-based heuristics. Is there a way to augment them with some random sampling and perhaps reweighting that will at least make them statistically consistent? Okay, forget about forget about being optimal in terms of the number of labels. Okay, so that's an open problem, and it's people have thought about it, but it's tricky. Okay, so that's one open problem. Okay, so these are sort of the practical schemes and sort of generic failings, why it's not been possible to prove things about it. Even the most basic property is failed by these methods.
But is it true that in this case you can't get any guarantee? Probably, you can argue that you won't get the optimal error, but maybe you'll get at most twice the optimal error, or something like that.
So what's happening in this case is that at some point in time you have found a boundary. Okay, and that's your current boundary, and there's a cluster of points far away from the boundary, and you never ask any questions about that cluster because it's far away from the boundary. You're sure all of those are sports documents, but actually they're politics. Okay, and this can be arbitrarily bad. Right? This could be. It really depends on how big that cluster is. Okay. So what do the sort of methods that theoreticians have cooked up look like? Okay, so So let's again stick to this case of one-dimensional data where the data lies on the line. Each classifier is a threshold. On one side is plus, the other side is minus. This has a VC dimension of 1. We know that in order to learn a classifier with error epsilon, error at most epsilon, in regular supervised learning, we need 1 over epsilon labeled points. Okay? If we want error 1 over a million, we need a million labeled points. Now, for active learning, what we would do is we start with those million unlabeled points, and we just ask for the label in the middle. And if it turns out that that's a plus, then we know the boundary has to lie on that side. And so then we ask for the 25 percentile point and so on. Okay? And in this way, the number of labels we need is just log 1 over epsilon. Okay, so we're literally down from a million to log of a million. So what this scheme is doing is that it's not committing to any classifier at any given point in time. It's just maintaining the version space. Right? It's saying initially the boundary could be anywhere. Now I've limited to this much. Now I've limited to this much. And in this particular case, it's able to shrink the version space in half, literally each time. Okay, and so that's how it works. Now, of course, this is just for points on the line. But over the years, over the past decade or so, people have extended this idea to many other hypothesis classes of interest. Okay, linear separators in d-dimensional space, all sorts of different classes. Okay, and for these other classes, it's not necessarily the case that each query will halve the version space. You know, sometimes the amount you cut off the version space with each query is a little bit smaller. But still, in general, there is this exponential shrinkage where the dependence on 1 over epsilon, you know, very often shrinks to log 1 over epsilon. Okay? So, okay. And so there are many different algorithms of this type. Okay? So this is sort of the state of active learning. And as I said, unfortunately, there is a basic problem with this whole model. And so let me just explain what that is. It's the following, okay? So let's say you get this new data set, and you're in this situation, you have 1 million points, you can only afford to label a few of them, but you want to build a classifier. So you say, okay, I'm going to build a linear classifier. Let me find the best active learning algorithm for linear classifiers. So you get the algorithm, you know, it's super, you know, it's super careful about which points it picks. You pick 1,000 points, and you get a linear classifier that you are assured is close to the best linear classifier. So you get this linear classifier, you're gratified, and then after playing around with it a little bit, you realize that it's actually got 10% error. Now you know that you can't really do much better as far as linear classifiers go, but at this point you decide, you know what, I think I actually need a quadratic support vector machine. So then you pull out the active learning algorithm for quadratic support vector machines, and you start running that. And that also asks for 1,000 labels, but those 1,000 labels are different because all of these algorithms are fine-tuned to specific hypothesis classes. So it asks for a different 1,000 points, and then you get the quadratic boundary. And then you realize, oh, actually I need a neural net. Let me find the best active learning algorithm for neural nets. And then they say, well, you know, actually the best active learning algorithm depends on whether you want 1 layer or 2 layers. Or 3 layers, and how many nodes there are in each layer. And so this goes on. And so this procedure is really not, I mean, this problem formulation is not compatible with a kind of typical way in which classified development takes place, where there's these iterations in which, you know, different models are tried. Okay? And so what I would like to suggest is a variant of the problem that you can call active annotation. And here, the final product is not a classifier, but a full labeled data set. Okay? So you start with your collection of unlabeled points. You don't know anything's labeled. You provide some parameters, epsilon and delta. And there's a human expert who can answer any query. Now the algorithm begins. It asks all sorts of questions, but at the end, it has to produce a fully labeled data set. So it asks for some labels, and it fills the rest in by itself.
Can I ask you a question? The human expert is trusted?
Right. So there are some models in which the human expert is allowed to be noisy, and
According to some distribution, he's not a worse case or something?
So, there are different noise models. One thing that so if you look at the completely noiseless case, a lot of those results extend very easily to benign forms of noise, where on any given instance there is a certain probability of giving the right answer and a certain probability of giving the wrong answer, and the probability of giving the right answer is greater than the probability of giving any particular wrong answer, if there are several choices for what.
They're independent, the queries. This probability of error isn't.
Yes, yeah.
So it's memoryless, this expert.
Right. So that's the sort of noise model that is generically easy to handle in as far as labeling goes. So does the problem formulation make sense? You're given the epsilon delta, the algorithm asks some queries, fills in the rest, and the guarantee it has to give on the data set is that now, with probability 1 minus delta over the internal randomness of the algorithm, the data set is sort of epsilon pure. At most, an epsilon fraction of the labels are wrong. Okay? And of course, you want to minimize the calls to the human expert in producing this. Okay. So once you have a data set of this kind, then you can try all sorts of different types of models on it. Okay, does that make sense?
So the difference is that you're not committing to any type of classifier in this problem.
Right. You're forced to label the entire data set.
But any classifier would also allow you to label the entire data set, right?
Right, but a priori you have no idea whether you would get an epsilon proxy. And what we'll see is that methods for solving this problem tend to be fairly flexible in the kinds of values. Yeah.
So in the active learning setting, you still have the same sort of input and this, and you want the generalization error. Isn't that related to this, or how is that?
In the active learning setting, all you can guarantee is that you're at most epsilon worse than the best linear classifier, say.
Oh, okay.
Whereas here you're forced to you're forced to produce a good data set.
Okay, Sanjoy, one quick question, just to follow up on that question. What if you fix a hypothesis class, and once the version space is below epsilon about, you decide, okay, I pick whatever hypothesis is left, label everything, and then use that as your labeling. So with some high probability, you would have labeled with error fairly close to epsilon.
Yeah, so if you start with a particular version, if you start with a particular hypothesis class, and you get lucky in the sense that there is some hypothesis in that class that is fairly good on the data, then you can just use an active learning algorithm for that. Okay, so I'm going to talk about the work that's been done on this, and some of the methods I will discuss are from the early 2000s. Some of them are very recent, from this year. Okay, it's going to be I'll basically focus on the open problem, since much more is open than known. Okay, yeah. Go ahead.
So after the intro, the slide you just set up is the way you think is the right way of doing it, and the other ways are wrong?
Yes. So
Okay.
that is correct. But later I will introduce an even more general version of this problem, where the feedback from the oracle consists not just of labels, but of richer information as well. And this is a sort of a very exciting area of research. Okay. Okay, so we have the active annotation problem, and I'll talk basically methods over here. There are two broad classes of methods that have been pretty successful, both on the theory and practical side: graph-based methods and cluster-based methods. And so I'll spend a little bit of time talking about these. So how would you even solve this problem? Okay, so here's a really simple baseline. So you have this data set, you're forced to label all of it. Why not do this? Pick a few points at random, get the labels, and fill in the rest using nearest neighbor. Okay, so you get labels for 1,000 points. You actually have 1,000,000 minus 1,000 remaining unlabeled points, and for each of them, you look at its nearest neighbor amongst those 1,000, and you fill in the labels. Okay? That's fairly reasonable. Okay, what's wrong? Okay, so how can we improve upon this? The first is to do more intelligent querying. Okay, instead of picking 1,000 of those points at random, you could maybe pick 1,000 of them that are spread out in some way. Okay. The second is that methods like nearest neighbor, non-parametric methods of this form, don't have great rates in high dimension. Okay, and so ideally, what one would like is something that is more adaptive to underlying structure in data. For example, cluster structure or manifold structure. Okay, so for example, if the data looks like this, and these are the two labels you've got, then, and you want to figure out the label for this, maybe you should look at the manifold structure rather than looking at the nearest neighbor. Okay, so there is a very nice algorithm that incorporates all of these ideas, has been, by all accounts, rather successful in practice, and for which, sadly, the theory is not developed at all. So I'll tell you what it is. It's a very simple and nice method. This is due to Jerry Zhu, Zubin Gharamani, and John Lafferty. Okay, and it's from back in 2003. Okay, so it's been 15 years. People still haven't figured out exactly how to say, how to say good things about this. It's a very nice method. Okay, so here's what happens. You've got your n data points. You build a neighborhood graph on them. Okay, so you connect each point to its nearest neighbor, something like that. This is basically adaptive to manifold structure. Okay, so because the nearest neighbors in Euclidean space are, roughly speaking, also the nearest neighbors on the manifold. Okay, that's the if you look at local regions, Euclidean and manifold are basically the same, and so that's the intuition behind these neighborhood graphs. So you do this, and now let's say that you get a few labels. How would you fill in the rest? So you find out that this is 1, this is 0, this is 1, this is 0. How would you fill in the remaining labels? And what they suggest is to do it by solving a very simple optimization problem. So they said, okay, let's introduce a variable for each label. This is going to be F1, this is going to be F2, this is going to be F6. Now the labels we know we're going to constrain. So F9 has to be equal to 1. F8 has to be equal to 0, and so on. And everything else can be any real value. It doesn't even have to be 0 or 1, okay? It has to be any real value subject to minimizing this smoothness cost function. We just want it to be the case that neighboring points are unlikely to have different labels. Okay, so we charge a penalty when neighboring points have different labels. Yeah.
Isn't this basically solving a linear system constrained to those points?
Right, this is just a least squares problem. Okay, so this is a least squares problem. It's got a nice closed form solution. Okay, and it's not hard to see that in fact all the numbers that it fills in are going to be between 0 and 1. Okay, so you solve it and it's going to give you numbers like this, and then to actually classify you threshold. You could threshold it at a half, but there are actually other variants. If the classes are imbalanced, you would want to threshold in a slightly different way. Okay, so this is how you would fill in the labels, and it turns out that these numbers have a nice interpretation in terms of random walks. Okay, this is something that's easy to check. Basically, what does this 0.7 mean? Well, suppose you were to start a random walk at that node, where you choose a neighbor at random and you go over there and you keep going until you hit a labeled point. 0.7 means that you have a 0.7 probability that the label point you end up with is a 1. Okay? And so over here, there's only a 0.1 probability that you would end up with a 1. Okay, so it's got this nice interpretation. Yeah.
What's a good choice of these initial label points?
Right, so that's, yeah, so this is just, so that's, we'll get to that in a second. Yeah, so how do we choose these points, right? Because as with any active learning scheme, it's going to be adaptive. So we're going to use these numbers to then figure out which one to pick next, okay? Okay, so this is the overall setup. Yeah.
So effectively, doesn't it boil down to you want a cut where you basically the ones and zeros are separated and you're minimizing the number of edges that are cut, or maybe the conductance?
Exactly, yes. So it is minimizing some sort of continuous approximation to cut size. Yes, it's something like that, right? So, okay, so but what's the active learning scheme? So now we know that if we have a few labels, we know how we're going to fill it in, okay? So what's the active learning scheme? Well, at this point in time, let's quantify the overall uncertainty. And we'll say the uncertainty in here is 0, because we know the label. The uncertainty for this one is a 0.1. The uncertainty for this one is a 0.3. The uncertainty for this one is a 0.4. And we add up all those uncertainties. And that tells us the uncertainty of our current configuration. Okay, now the way we decide what we're going to query is the following. Okay, we say, okay, well, what would be the benefit of querying, say, this one? Well, we don't know what its label is going to turn out to be, but we think it's got a 70% chance of being a 1 and a 30% chance of being a 0. Let's say it turns out to be a 1. Let's resolve the linear system with the 1 over here and see what uncertainty ensues. And let's resolve the linear system with a 0 in here and see what uncertainty we get. And then we weight that like 0.7 and 0.3. And that tells us how the uncertainty will change in expectation if we label that point. Okay? And so this is how it proceeds. So it's sort of greedily trying to reduce the uncertainty as fast as possible. Very nice algorithm, very intuitive, and as I said, by all accounts, it seems to work well. So what can we prove about it? Can we show that it, has good rates of convergence? So no, unfortunately, it's not even consistent. Okay, it's just running into the same problem again. Okay, and so why is that? Well, let's say we had 3 labels. Okay, what values would it fill in for the rest? Well, over here, if you were to start a random walk here, you would hit a 1 with probability 1. So it would fill in 1s over here. Okay, and so the values it would fill in over here are 0.5, 0.25, 0.75. Those are the random walk probabilities. And over here it would fill in 1s, which means it would never query any of these points because it's completely certain that's a 1. Yeah.
Why was that the definition of uncertainty you use compared to like maybe something more entropy-like, or like is that lack of consistency like linked to the particular choice you made in the functions?
Right, yeah. So there is, right, so, okay, so there, right, so, so there are different notions of uncertainty one can come up with, right? And the problem is that when you have a limited number of labels, any notion of uncertainty you come up with is going to be, way off. Okay, it's in fact harder to estimate uncertainty than it is to estimate labels. Okay, so these uncertainty estimates are going to be very inaccurate, and the only thing you can hope is that as time goes on and you get more labels, the uncertainty estimates actually get better. Okay, and so the question is there a way to modify these schemes that take into account that take this into account? Okay, yeah.
Does somehow epsilon random helps like in getting away with all this? So there's always an epsilon probability of randomly picking an element and having a label.
Yeah, so that's a good question. So the question, like, if we were to, basically every few steps just pick one at random, right? Just pick a label at random. Would that solve the problem? And that's not known. So that's So one very nice open problem over here is just to fix this, okay? This is a lovely algorithm. It's intuitive, but it's not even consistent, okay? It really feels like there's something you can do that's fairly close to this in spirit that will be consistent and will, and will have reasonable rates. And what is that, okay? People have thought about this, and I will give you, I'll show you one of the things that was suggested, and it's very different in spirit from this algorithm. Yeah.
People have tried sampling from that distribution, right? At least as opposed to choosing the one that minimizes, or sampling from the squares. There are lots of different
Right, yeah. So the distribution over here is basically a kind of Gaussian random field because these things are allowed to be continuous. So one can sample from that, and there is a version of this that does that. And it's not clear whether that...
Nothing is known.
Nothing is known at all. Yeah, actually, this... yeah.
What about adding random links to that graph?
Sort of dense, making the graph a little more dense?
Well, I mean, it's not the density issue, it's about random. Like, now you have the path. If you add, let's say, a random matching between the vertices, it's going to become 3 regular. You have short paths, so this cut structure will cease to exist, and maybe.
Yeah. So that would be interesting if there was a way to do that both maintain the benefits of having a neighborhood graph, which is the preservation of this local structure, and yeah. Okay, so this is one open problem. So as I said, this algorithm was from 15 years ago. But 2 years ago, a group of people came up with, finally, a suggestion for an algorithm like this, which does have some nice properties. And so I'll tell you what that is. And this is by Gautam Dasarthi, Rob Nowak, and Jerry Zhu. Okay, and it's also a graph-based algorithm, and it has a very, and this. This has nice rates of convergence and guarantees and so on, which we'll see in a second. Okay, so what is this algorithm doing? Okay, so again, you build a neighborhood graph. Over here, the graph happens to be just this 2D lattice. Okay, these are the edges, and let's say that we have the ones in the middle and the zeros outside. Those are the two classes. What this method is trying to do is to identify all the cut edges. The edges that cross between the two classes. Okay, so the goal of the method is to identify all of these edges. That's what it's trying to do, and it thinks of that as its goal. It wants to get to that goal as fast as possible. Once you think of things that way, a whole lot of fairly intuitive methods suggest themselves. If you want to find cut edges, hey, why not do something like this? Initially, you don't know where the zeros or ones are, but randomly sample a few points until you get at least a 0 and a 1. And now you know that on any path connecting those two, you have a cut edge. So you can kind of do a binary search on that path and very quickly locate one of the cut edges. And if there's another path, you can do a binary search on that path and locate the number of cut edges. And this way, it seems that if you're not thinking of, apart from the random sampling, you're literally, the time it takes to locate each cut edge is just binary search on a path. It's like log the diameter of the graph, something like that. Okay, so it seems like a method like this would have a label complexity that depends on the number of cut edges, the log the diameter of the graph, and in order for this random sampling to work, what also matters is the proportion of each class. Okay, and in fact. And it's sort of clear that this is both, that something like this would be sufficient. So let me tell you what the method is. It's a very nice method. Okay. So what it does is it starts with this, and then it keeps, whenever it's stuck whenever it's stuck, it does random sampling. Okay, and whenever it has 2 points of opposite polarity that are connected, it looks for the shortest path between 2 points of this type and queries the midpoint of that path. Okay, so let's say that it starts by querying these three. So let's say it starts by querying this point over here. It's a 0, okay? Next queries that point. That's another 0. And then it queries this point. It's a 1. Okay, finally, we have 2 points of opposite polarity. Now let's look at all shortest paths between points of opposite polarity. So there's this one path over here. Oh, that's very long. But this is the shortest path over here. Okay, or actually there's several shortest paths. And let's query the midpoint of that shortest path. Okay, so it queries the midpoint. So it gets this point over here. And it finds that that's a 0. Okay, now again, it looks at all shortest paths between points of opposite polarity. And now the shortest path is just this. So it queries the midpoint of that path. Okay, so it's going to query this one next. And now it has located a cut edge. Okay, It's found this cut edge, and it's just going to remove it from the graph. Okay, so it's found this cut edge, it's going to remove it. And now, again, it looks at shortest points between all pairs of opposite polarity, and it's going to query that one and find another cut edge. Okay, does that make sense? Very nice algorithm, right? So what were they able to show? Well, I think it's the sort of the kind of bound they get is exactly the sort of bound I was outlining earlier. That there's a certain charge for random sampling, and then basically it's the number of cut edges times the log diameter of the graph. Okay. The case they look at is where there are k nodes adjacent to cut edges. And if you were to remove the cut edges, you might not get just two connected components. You could have several connected components. And so it matters how many there are. Let's say there are m connected components, and they each have size beta times n. So they each are fairly large, and the diameter graph is delta. Then this is the number of queries you end up making. Okay. So, so the question is, what does this translate to in terms of statistical rates of convergence? Is this truly sublinear? Okay, and that's also something they work out. And this is what they find. Okay, so if you were to just do passive learning, non-parametric learning in d-dimensional space, the error rate looks, under a smoothness condition, say the function you're learning is Lipschitz, looks like n to the minus 1 over d. That's really bad when d is large. Okay? What that means is if you want error epsilon, you need about 1 over epsilon to the d points. Okay? And I mean, I can briefly indicate why that's the case. You know, if your domain looks like this, let's just say we're in 2D. Let's say we're in high dimension. And all you know is that the function you're learning is Lipschitz, and you want error epsilon. Well, basically, you have to create this grid of size epsilon. Okay, you've got to create this grid, and you need maybe a couple of points inside each grid box. Okay, and that's why you get you need n to be about 1 over epsilon to the d. Okay, if all you know is something is Lipschitz. So that's sort of necessary and sufficient. Okay, and what these people are saying is that they get something that's a little bit better. Okay, and so let me explain what this is. So what they do is they say we're going to have a smoothness condition on the boundary. We're going to think of the boundary as being not a d-dimensional object, but basically a d minus 1 dimensional object. Okay, so let me just come over here. You know, in the 2D setting, you could have a crazy decision boundary that sort of fills up the whole space, right? But what they're saying is no. If you were to divide, if you were to create a grid, then the boundary intersects only a small number of cells of this grid. Okay, and so in the 2D case, if you have n cells, it'll intersect about square root n of them. Okay, it's n minus 1. In 3D, it'll be n to the 2/3, and in general, it'll be n to the minus 1 over d. And we know that this method, the number of queries it asks, is literally going to be proportional to the number of boundary cells, ignoring logarithmic factors, the log diameter. And so you do get something that is sublinear, but only very slightly. Okay, so it's, instead of n, it's n to the 1 minus. Instead of querying all n points, it queries n to the 1 minus 1 over d. Okay. So what can you? So this is sublinear. It's good. There are, you can show that you can't do any better than this. But obviously, this is not good news in the sense that one would like to query much less than this. And what could one do? Because if the dimension's high, like 1,000 or 10,000, then this is not saying much. Yeah.
But in a non-parametric setting, you can't beat this because that could be the cut size, right? And they are outputting the cut explicitly. So unless you make some assumptions on what the function is, you really can't beat this.
Yeah, absolutely.
So is like assuming the data is uniform over 0, 1 to the d, the right thing to think about? I mean, you started with these non-uniform data sets, and this is what motivated like a lot of this work. I mean, it seems like this is the wrong setting to be analyzing. I mean,
yeah.
Clearly it leads to these bounds, right?
Right. So yeah, assuming the data distribution is uniform or 0, 1, 2, 3, that's crazy, right? But it turns out that the bounds are, if you were to instead assume that the data distribution is simply bounded below in this, bounded away from 0 in this the same range, then you get something similar.
But if you start by with the graph is the nearest neighbor graph on a data set in a high dimension where the degree is k, which is much smaller than the dimension, do you get rates dependent on k instead of d, or?
Right, so the sort of thing that you can hope for is if you say that, right, it's this, so having a data distribution uniform over 0, 1, 2 to d means that the data fills up the space. So a different assumption is that the data lies on a low dimensional manifold, or that the data lies in a set of low doubling dimension. And if that's the case, then you can get the same rate where this is replaced by the doubling dimension. And in fact, we'll see that very soon for a different method. Okay, so that's one thing you can hope for. It's one kind of structure that you can hope to be adaptive to. There have been a lot of bounds proved of this kind simply because we have these nice formalisms like doubling dimension. But there are other types of structure that we would like to capture, like cluster structure and so on, for which we don't have these sort of nice indices, and as a result, nobody's proved too much about it.
Yeah, with some further assumptions on the neighborhood structure, could you do dimensionality reduction and then try these methods?
Oh yeah, that would be interesting. Right, if there was some sort of a generic reduction of that type. So certainly, in the manifold case, it's known that if you have data that's in a, so this is something that Clarkson showed following Wakin a few years earlier, that if data lies on a k-dimensional manifold, then even a random projection to k over epsilon squared dimensions preserves all distances within 1 plus or minus epsilon, as long as the manifold's curvature is bounded in some sense. Yeah, that would be. Okay, so this is so these are the positive results. Okay, and this method is very different in spirit from the other one, and unfortunately, in practice, doesn't work as well. Okay, but why is that? Because it's actually very clever. It doesn't seem to be losing out a lot. It seems very optimized, and the problem is that it's optimized to find all cut edges in the shortest time possible. That's what it's trying to do. So if that was the task if that was the task, then it's perfect for that. Okay. But what usually happens is that you stop the process long before you found all the cut edges. You aren't able to. And this does not gracefully decay along the way, whereas the rival method is greedily trying to reduce the uncertainty on every single step. And therefore, and therefore is looking better along the way in some sense, okay? And so it would be very nice to somehow fix this, This is just yet another case where, active learning, theory and practice have got this wide divide between them. Okay, so any questions about that?
So, yeah. Just to understand the question better, so is it that in general you really don't care about the cut? You really care about the error in classification. So let's say the cut was a little wavy and you just said it was straight, that's probably still good enough, right? So is that...
That's one issue. And the other thing is that you can expect to stop long before you're able to get the cut. And so like how would you what could you do in anticipation of that? Okay. So quite successful in active learning. And here the theory and practice are perhaps a little bit closer. Okay, these methods are just childishly simple. So this was a method that I suggested with Daniel Su about 10 years ago. And by that time, I had been doing quite a lot of work on active learning, coming up with some very sophisticated and clever algorithms I was very proud of. And this just almost seemed like a joke in comparison, because it was like so simple and obvious. And I think this is the only one that people have ever used. It's the only one anybody ever asks about, or like wants the code for, or and so yeah. I mean, I can tell you a little bit about it. So the idea is just ridiculous. Okay, so like, hey, let's say the data looks like it's got 5 clusters. Maybe we only need 5 labels. 1 label per cluster, and we're done. Okay, so that's the starting point. Okay, okay. Now, obviously, we need to be able to adapt to any data. So, maybe the cluster structure will not be so clearly defined. Maybe the clusters are not pure. We have to be sort of mindful of that. So let's do things this way. We have the unlabeled data set. Let's start by clustering it. Maybe we get 2 clusters. And now here's the key thing. We are going to randomly sample a few points within each cluster. We're not allowed to say, I want to ask for that label. We're just allowed to say, give me 3 random points of this cluster. Okay? So we choose a few points at random, and we get their labels. And now this looks pretty pure. And so I'm feeling good. In a pinch, I would just label the whole thing red and not worry about it. Okay? But this is not looking pure. So what do? I cluster it some more. I further partition it. And now what has happened is that because I had chosen these points at random, because they are random points in here, they're also random within these clusters. And so I can reuse the labels. That's it. That's all that's going on, right? And you can just keep doing this. And so one way to think about it is you start with a hierarchy. You pick a few points at random over there. You sample their labels, and if it's not pure, then you move down to the next level. And now you look here, and if that's pure, that's fine. Otherwise, over here, you move down to the next level. Very simple. Okay?
You ignore labels when you cluster? You only look at where they are? Yeah,
so here, so this is a very simplistic scheme where the clustering is just done in advance. The hierarchy is built in advance, right? So yeah, how do you build a hierarchy? How do you decide? At any given point, there's several clusters where you could pick a query. Which one do you pick? And how do you decide when a cluster is sufficiently impure that you would move to its child? Okay, so 2 versions of the scheme, or maybe some more have been analyzed. In our earliest paper, we just made the simplest choices. Just said, what hierarchical clustering do you use? Well, let's just use the most popular hierarchy cluster algorithm, Ward's method. Which cluster should we query? The one that's the least pure, why not? Okay, and when do you move down? When confidence intervals indicate that the cluster is highly impure. Okay. Later work by Ruth Turner, Sharon Wolf, Shai Ben David, and Samori Patoufé looked at, were able to give nice generalization bounds for this. And for example, one of the things they did was to not just have any old clustering algorithm, but they said, okay, let's come up with a tree structure that is provably adapted to structure in the data. So for example, it's known that if you have a random projection tree, which is kind of like a KD tree, but at each given point you pick a direction at random and you split, and you build a tree in this way, it is adaptive to the doubling dimension of the data. Okay, and so and so on, and for that they were able to get rates that would look roughly like this, but with the doubling dimension in place of the actual dimension. Okay, so okay, so this is a scheme where yeah, I'm not going to go into the experiment. Basically, it seems to work fairly well. I think the open problem over here is is to come up with the right decision for what to cluster and when to move down. And that's just not been figured out. Okay, so there's and optimizing that would make a huge difference in practice as well. So even the sort of silly, random initial choices that we made end up doing fairly well. And optimizing that could make a very, very large difference. Okay, so that's an open problem over there. Okay, so in the few minutes that I have left, I just wanted to talk about something that we're working on much more recently, and is a very interesting area these days, and that is to move beyond labels. Okay, so machine learning systems, for the most part, have relied only on labels. All we ever give them is labels, pluses and minuses, and all they ever give us back is a classifier that gives labels. And all of a sudden there's a interest in making things, having the interaction be a little bit richer, where we don't just label stuff but give simple explanations. And in return, the classifier also returns simple explanations. Okay, so how would this play into the annotation problem? So here's an example. Okay, so the expert is asked to annotate a document and looks at the document and says that's sports. In addition, since the human has read the document, he also highlights a couple of words, like a wicket keeper, okay, that are highly indicative of the document label. Okay? Or a computer vision system gets the latest photo uploaded by a bird watcher and says, oh, look at that, that's a canary. And then the human expert says, no, it's not, it's a warbler, but at the same time provides a little bit of an explanation by, say, clicking on the beak, or something that distinguishes these two types of birds. Okay, so these are both cases in which the labeler is doing a little bit more work and providing some information that's potentially ambiguous. Okay, so over here it's providing a word like wicket keeper. Over here it's clicking on the beak, and it's like, what does that mean? Is it the color of the beak? Is it the fact that there is a beak? Was he actually clicking on the head and did the beak by mistake? It's ambiguous, but it seems like it could be super helpful. Okay. And so it's of interest to sort of formalize this and see how this helps with annotating data sets quickly. Okay? And so the work over here deals with formalizing the semantics of this kind of feedback, quantifying rates of convergence with feedback, and to be honest, it just reshapes the landscape of what is learnable. So for example, one thing that we're going to show in the conference later this year is that you can learn disjunctive normal form formulas with this kind of feedback over here. Okay, so this is a type of formula that Valiant, started talking about in his original PAC learning paper because he thought it was something that's very natural for humans. It's a very natural way for us to express concepts, and yet it turned out to be hard to learn. But once you allow a few explanations, then it becomes much easier to learn. Okay, so so let me just finish with a modification of the annotation problem. Okay, so this was the original annotation problem, that we have an unlabeled data set of endpoints, and we are able to query individual labels. A modified problem is that either a human or some other system has also given us a collection of weak rules. Okay? These rules might be things like, oh, if it contains the word wicket keeper, it means it's sports. Okay, that's an example of a weak rule. And these rules don't apply to every instance. This only applies to documents with the word wicket keeper. It's a weak predictor. Sometimes it's wrong. Okay, so it's a weak rule, but we have a collection of weak rules like this. And so for example, each weak rule could even be a crowdsourced worker, a worker that occasionally abstains, and when it doesn't abstain, makes a prediction that's sometimes wrong. How can we use these to rapidly label a data set? And currently the system, so for example, there's a system by Chris Ray at Stanford called Snorkel that's very popular, that basically allows people to specify weak rules. And for any given document or instance, there are many rules that potentially apply to it, saying possibly conflicting things. how does one resolve this? And they just have an ad hoc way of doing this. It would be very nice to kind of work this out more carefully. You can think of this as a generalization of the crowdsourcing problem that also applies to annotation. Okay, so I won't go into more work on this. So yeah, so I think some interesting open problems are on the graph-based annotation side to just look at the Zhu-Garamani-Lafferty algorithm and figure out what needs to be done to it to make it good, to make it statistically good. On the cluster-based annotation side, I think a very nice thing is to figure out a good protocol for hierarchical sampling. And for this richer feedback, this is sort of a new and growing area right now, and there's just a lot of formalization needed. Okay, thank you.
Yeah, we have time for a question.
So in the graph and also the cluster-based annotation, it seems like you're labeling all the data, and maybe this implies an actual classifier that might generalize to new data that isn't in the set yet. But it doesn't seem to come from like a nice class of functions, a nice function class. Is this the problem with generalization?
So right, so both of these methods work best if there is some nice structure in the data, and it's not necessarily corresponding to sort of a classical concept class like a linear separator or something, but just some sort of cluster structure, this kind of manifold structure, and so I think it's of interest just to formalize some of these different types of structure, and then and see how they.
So, so is your answer saying that you think that there is an underlying function class that they're following that should be formalized, or that you should enforce another function class on it, or you should not worry about it?
Right. So I think that for either of these two methods, I don't think it's necessarily useful to formalize a single function class that they seem to be tailored towards, but rather to formalize a variety of different types of structure that they are adaptive to.
Okay.
So something like that.
Let's thank Sanjoy once more. Thank you. So we'll come back at 2, and I also just want to